Hello everyone, this is Abhishekta from IISER Mohali, and today we would be discussing about the hydrogen atom of statistical mechanics. And if you guessed that right, yes, we are going to talk about the Ising model. The Ising model was originally invented by William Lenz, who was Ising's professor. Ising was a graduate student who was working on this model for his graduate dissertation. To understand the classical Ising model, let us try to understand something called the spin systems. Now, say for example, if we take a magnet having north face pointing up or the south face pointing down, and if you take two magnets and you try to approach them, what happens is they will always try to anti-align. So that means this first magnet is trying to force the second magnet to change its direction. Let us get some variables, say sigma 1 and sigma 2, which indicates their direction, like in which direction the north is pointing or the south is pointing. So we can always write the interaction between them as follows: sigma 1 and sigma 2, and since they are anti-aligned, so that is minus sigma 1 and minus sigma 2. Now let us say another magnet approaches them. So I can then write the whole configuration as minus sigma 1 minus sigma 2, then I'll again introduce minus sigma 2 minus sigma 3 and something like that. Now what I can say is, instead of this, if there are n magnets, I can write it as summation of sigma I, sigma j, and then with a negative sign before it. Now let us say, for example, to make the system more complicated, I wished I took a wall and inserted it in between. Now I have the full potential to actually control the interaction between these two magnets. Now let us label this the strength of this wall as Jij. So what happens? Our new interaction term that becomes minus of Ij, j of Ij, and then sigma I, sigma j. Now again, what we will do is, for further complications, I introduce a magnetic field, that is B over here. Due to the magnetic field, these individual magnets experience some force. Now, we can write down this force in a single magnet as follows, that is minus of sigma B, sigma I, summation over I. Now, this is what the net Hamiltonian should look like. For your information, Hamiltonian is actually the total energy of the system. So, my net Hamiltonian is H is equal to minus of sigma Ij, then Jij, that is sigma I, sigma j, then minus of summation over I, B, sigma I. Now, if my j is actually positive, if my j is positive, I can say that my system is aligned in the same direction. That is, my system is in a lower state. But if my j is negative, my systems are anti-aligned and they are at a high energy state. Classical model, Ising model is special because despite being simple in description, the model exhibits rich features like a phase transition, symmetry breaking in the ferromagnetic phase. Near criticality, the model can be applied to a surprising number of different systems. This feature is known as universality, where the same theory applies to all sorts of different phases, transition like liquid gaseous system, magnets, superconductor, and many more. Calculation of partition fraction. Now partition function is equal to Z, that is summation of Si, where Si are spin states, and e to the power minus beta ESI. The issue is that the partition function cannot be calculated analytically for general lattices in arbitrary dimension D. Exact solutions of partition function for Ising model are known for D equal to 1 and for D equal to 2 only when the external magnetic field is 0. For D equal to 3 and for D equal to 2 in presence of external field, the solutions are not determined exactly. We would use mean field theorem to solve this. The mean field approximation assumes that the fluctuations of spin away from the average are small. So we come up with EMF is equal to half JNQM square minus JQM plus B summation of SI. Now our new B effective is JQM plus B. What we will do over here is, we would take two cases, B equal to 0 and T varies, B not equal to 0 and T varies. If B equal to 0, we obtain a graph of magnetization and temperature as follows, where we observe that magnetization suddenly drops to the value 0 at a temperature Tc, that is Curie's temperature or critical temperature. M's value is can be plus minus 1 both. When B does not equal to 0, the case is rather different. We do not obtain a sharp turn like the B equal to 0 case. Rather, we obtain something like this, where when B is positive, M is plus 1, and when B is negative, it's minus 1. To calculate the critical temperature in 2D Ising model, we would use Cramer's proper duality. At low temperature, the partition function is dominated by the lowest energy states. At high temperature, it is dominated by maximally disordered states. Yet comparing the partition function at low temperature and high temperature gives us some interesting results. Now we obtain something like this. KBT is equal to 2J by log 2 root 2. This was what we obtained from Cramer's result. We equated the partition fractions for high and low temperature. Now we will see some Monte Carlo simulations. We would actually change the temperature such that it is always below the critical point and observe how the spins are changing. So this is the Monte Carlo simulation which I wanted to share with you. So what happens over here is So what happens over here is, we chose the temperature as 3 and then the recording time as 50,000 and then the lattice size as 400 into 400. Now for the step 0, we can see that there's a lot of blue and there's just some drop of red color. Now these red are spin down states and blue are spin up states. Now as my steps are like Monte Carlo steps are increasing, I can see the red abundance is also increasing. Now why is it so? So the temperature is actually increasing a little by each step of the simulation. So I can see that as the temperature is getting raised, so does this abundance of red over here. So this is actually because the typical length scale of the cluster forming is called correlation constant, correlation length, and as it grows, as we increase the temperature, and it diverges at Tc. So what happens as we approach towards the critical temperature, this vanishes, this correlation length vanishes. So this is how it should look, and you can see like even for more steps over here, the step 108, as I can see over here, it's a lot, like blue and red are approximately equal to each other, but initially that was not the case. So yeah, this was what I had to illustrate. Thank you for watching this video and I hope you liked it.